But first, we have a thought puzzle. Look at example 1. Look at example 2. The tension in the rope in the bottom case is A, greater than, B, the same as, or C, less than the tension in the top case. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of your answer. So in the top case, we have 4 humans. Let's make them all identical humans so they all pull with the same strength, just to make the concept easier. And they're pulling on this post. In the second diagram, we have 8 humans. Let's again make them all identical humans pulling in opposite directions. The tension in the rope here compared to the tension in the rope here. The tension in the rope in the bottom is A, greater than, B, the same as, or C, less than the tension in the top case. Here we go. Who says A, Mr. Dewick? 8 people. It's got to be bigger. A, greater than, A. 1, 2. Who says the same as? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Who says less than? Because otherwise I was watching. Convince me. Matt.
When you're pulling against like whatever it's attached to, it's gonna do the exact opposite. Like if you pull one way, it's gonna pull.
Let's put some nice numbers here. This is one of my go-tos. If I can't see it, I'll make up nice numbers. Let's suppose these people are pulling with exactly 1,000 newtons. Are they accelerating?
No.
That must mean forces are?
Balance.
So how hard must the pole be pulling in that direction? Okay. Here again, they're pulling with 1,000 newtons. Are they accelerating? That must mean the forces are, I'm looking for where this starts to letter. So how hard must those 4 people in the other direction be pulling with? And Jaden, can you see if I remove the picture, the diagrams are identical. It's the same physics going on here. In one situation, it's an inanimate object. In another situation, it's the people. Now, that second one, twice as many people, looks like it should be twice the tension. No. It's the same. So explain your answer. How did we explain that? What? Okay, if you said Newton's third, you could write that. If you didn't know that, you're not allowed to write that. You would instead say forces come in. I would take that as well. You could also say, Liam, since we're not accelerating, forces must be, I'm looking for where it starts letter B. That's actually Newton's first. We used a combination of Newton's third and Newton's first to answer this. But it has to be. That has to be the same. We're going to spend a few days looking at types of forces. The first one we're going to look at a little bit more is the gravitational force. I snuck this in last day. So my symbol for the force of gravity, F for force, lowercase g for gravity. How do you calculate Fg? Who remembers from yesterday? It's also on your formula sheet. You calculate it by mg. We put a positive 9.8 in. We'll take care of the negative if we need to by going winner minus loser. Minus loser. Minus loser. Hi, late person. See how I timed that? Wasn't that good? Glad you made it. Here's the notes. What direction does gravity act? Sorry? I kind of like that, but in Australia, their down is our up. So I'm going to be a little fussier this time. I'm going to say toward the center. And that lets Australia work as well.
So Australia is upside down.
It's all relative. There is no upside down or right side up. See, this is where I get grumpy with people showing up late and interrupting my lessons. There you go. There's a handout for you right there, Ronan. What's another word for gravity? This you have to commit to memory. No, it's on your green sheet. What's another word for the force of gravity? Starts with the letter W. It's on your green sheet. What?
Wait.
No now. Wait.
Oh, wait.
No now.
Wait.
No now.
Wait.
No now.
Wait.
Oh, W-E-I-G-H-T. Okay. So if I ask you to find an object's weight, don't tell me kilograms. Tell me kilograms times 9.8. Yes. Don't tell me kilograms. That's a hint. Shelby the ballet dancer has a mass of 56 kilograms. What's Shelby's weight in newtons at the Earth's surface? I said at the Earth's surface because it turns out you'll learn next year as you go further from the Earth that G, that 9.8, gets smaller and smaller and smaller, but we don't have the skill to deal with that yet. How would I calculate weight? mg. So it's going to be 56 times 9.8, which is what?
548.8.
Is he right? 548.8?
Yeah.
548.8. I'll put the whole thing in this time. Just for, yeah. Units, it's a force. Okay. By the way, if you know an object's weight, how could you figure out its mass in kilograms? Just divide by 9.8. Okay. So the official SI unit for mass is kilograms. The official SI unit for weight is newtons. In the imperial system, the official unit for force is pounds. So given that 1 kilogram of mass corresponds to 2.2 pounds at the Earth's surface, what's Shelby's weight in pounds? And that it would be correct. You can say weight in pounds. If you say weight in kilograms, I'll give you the stink eye. Because kilograms is not weight, it's mass. Pounds is weight. How would I convert 56 kilograms to pounds? Am I going to times by 2.2 or you know what? This is a good chance for us to review our dimensional analysis. I'll write down what they gave me. I remember that trick. And then I want kilograms to cancel. So where's it going to go in my conversion factor? Yep. What's going to go on the top? And I abbreviated pounds with the pound symbol because that was nice and short. And I guess it's going to be 2.2 pounds is 1 kilogram. You know what? I'm going to time this by 2.2, not divide. How do I know times? Because the 2.2 is on the top. I can probably do this in my head. It's going to be 112 plus 11.2. So it's going to be 112, 122, 123.2?
Yeah.
What would Shelby's mass be on Jupiter?
Well, what's the gravity?
Too slow. Arsh, what's Shelby's mass on Jupiter? What? Mass doesn't change. 56 kilograms, my friends. What would Shelby's mass be just outside of a black hole? 56 kilograms, my friends. What does change? Weight. That's the one that's location dependent. Then I need to give you the acceleration due to gravity at that location. On Jupiter, it's about 25. So if I want to find the force of gravity, and I'll put a subscripted J for Jupiter, it's going to be 56 times 25. What's a shortcut for multiplying by 25? I should do it times by 100 and divide by 4. So 5,600 divided by 4. So divide by 2, it's going to be 2,300. Divide by 2 again. 1,150? No, I'm way off. Or was I right? 14. Oh, I carried a 1 wrong. It does. It's why on a test, I don't do any math in my head. Yeah.
Did you, under the FG, what is that a J?
J for Jupiter.
Oh, okay.
I just didn't want to confuse that with my answer from A, right?
Yeah.
So you're starting to see how I organize things, okay?
Yeah.
So I will on tests and in the future, give you an object's weight in newtons. I've given you its mass. Just divide the weight by 9.8. How do you know it's a weight? Because it'll have a newtons next to it. The second force we want to talk about today is something that we call the normal force. Suppose a 12,000 Newton truck is sitting at rest on the ground. Draw a free body diagram of the forces acting on it. Okay, there's the truck. What are the forces acting on it? Get the obvious one. How big is the force of gravity?
9.8.
No, that's an acceleration. That's a bad answer. An acceleration is not a force. How big is the force of gravity? Exactly as a number. You know it. So you ready? Look up. Everybody look up. What units are next to this number? That's the weight. I gave you the force of gravity.
Yes, yes.
I didn't give you the mass. I gave you the weight. Is this truck sinking into the ground like quicksand, Jaden?
No.
Is it flying like Superman? So that means that vertically the forces must be, I'm looking for a word that starts with letter B.
No.
How hard is the ground pushing up? I'm going to write the word ground because FG to me means gravity. Oh, no. We're going to give this force a special name in just a second. Write F ground for now, but we're going to call the force of any surface pushing back against gravity, we're going to call it the normal force. Okay? Suppose we add a 2,500 Newton piano to the back of the truck. Draw a free body diagram of the new forces. Okay. What are the forces acting on this truck? Get the obvious one. Get the obvious one. How big is gravity exactly as a number in this question? Because they told me.
14.
No. That's all I'm saying is get the obvious one. The truck is feeling gravity pulling down with 12,000 newtons. What else is there? There is another downwards force on the truck, and that is the piano. Now, it's a bit awkward for me to try and write the arrow like that. So in a free body diagram, when I have two forces in the same direction, I'll just move one over. I'll put it beside like that. And that is 2,500 newtons. Is this truck sinking into the ground like quicksand? Is it flying through like Superman?
No.
I'm going to draw an arrow pointing up. Is the arrow going to be bigger, smaller, or the same size as the 12,000?
Bigger.
Why does it have to be bigger? How hard is the ground having to push up with?
14.
And I'll exaggerate it so it catches my eye.
That catches fire. Because of Newton's third.
Newton's first. Okay? Forces are balanced. Okay? Now, the reason it's the same size is it's a forces come in pairs phenomenon as well. And so if you argued Newton's third, forces come in pairs, I'd give that. This is a situation where both apply. I figured out how big it was using Newton's first. I figured out what was causing it because forces come in pairs. It's the ground pushing it. So I've called it F ground, but we're now going to say the force of the ground or any surface. Table, all of you right now with your non-writing hand, push against your lab table, push down, push harder. Can you feel the table pushing back on you?
Yeah.
Okay? We're going to give that force, the force of a surface pushing back on an object, preventing the object from sinking into it, a special name. We call it the normal force. The word normal in math means at right angles to, and the normal force always pushes up at a right angle to the surface. So if I push against this wall, am I sinking into the wall like quicksand?
No.
Am I flying off of the wall like Superman? If I'm pushing with 100 newtons, what's the normal force from the wall exactly?
100 Newtons.
And it would be, if I drew it, at a nice right angle to the wall. Right now, if gravity is pulling down on me with, do some rough math in my head, let's say 1,000 newtons of force, how hard is the ground pushing up on me with? Okay? Everybody right now, lift your feet up.
Oh.
Stop. Can you feel the chair pushing up on you?
Yeah.
Okay? The chair is pushing up on you right now with whatever mg is pulling down. If you want to calculate the normal force, you're never going to get an equation for the normal force. I don't have one, but you can figure it out because since you're not sinking into the ground like quicksand and you're not flying into it like Superman, the normal force must be the same size as mg. So if you know your mass times 9.8, you now know the normal force. Okay? Symbol, F with a subscripted capital N. You're never going to get an equation for the normal force, but I will ask you to find the normal force. How? This is a job for a free body diagram. Okay. There used to be for Physics 12 a provincial exam, and I spent a couple of summers marking that provincial exam. And one year there was a question that said, find the normal force. And I had a paper where the student wrote, which was funny, but they got a 0 anyways, okay? So at least they knew the symbol, I guess. But the normal force, as you actually pointed out, this is a, what we call reactive force. This is a Newton's third law force. What was Newton's third? Forces come in.
Pairs, not apples.
Because it's a reactive force, it's only as big as it needs to be. So, for example, now I'm pushing against the wall with 200 newtons. Am I sinking into the wall like quicksand? Am I flying off of the wall like, how big is the normal force? I'm pushing with 200 newtons. How big is it exactly?
200 newtons.
Now I'm pushing harder with 260 newtons.
Whoa.
How big is the normal force exactly?
260
Okay?
newtons.
So it will match you. It's a reactive force. It's as big as it needs to be. You can't get useful pushing out of the normal force. It's just what's matching you pushing against the surface. Okay?
Do it.
Sorry? It's the force that prevents us from falling into the ground. So right now, most of you are splitting the normal force between your chair and your shoes. And maybe a little bit with your elbows. Yes?
What happens when like it can't take?
Then the wall has to break and it will accelerate. So a bulldozer could exert a larger force than the wall was capable of rebounding, of matching. Okay, then the wall will collapse and break and the bulldozer will go through the wall. Newton's first will kick in.
Why do some things like have stronger force than like that wall?
That's cohesive molecular bonding stuff. It just has to do with the chemical bonds of the products that they're made out of. Yeah. Example 3. How big is the normal force in each of the following situations? Braden, what's this question asked me to find? Sorry? The normal force. This is a job for a free body diagram. Oh, wait. Did they give me a picture? Say yes. I'm going to be a bit lazy. Technically, a free body diagram, we're supposed to represent the mass, don't write this down, separately with a dot. But often, if they give me a picture, I'll be lazy and just label the picture itself, which technically isn't a free body diagram, but we're going to do that fairly often if they give us a picture. So, Braden, what are the forces acting on this 10 kilogram mass? Get the obvious one. And there is an arrow there already. I'm going to call it mg. Not only that, Braden, I can calculate it. What is the mass? What's g as a number exactly? What's g as a number exactly? I didn't say what's g rounded off roughly. Let's try that again. Scene 1, act 1, and take action. Braden, my clever boy, what's g as a number exactly? Hey, without a calculator, can you go 10 times 9.8 in your head? Or use a calculator if you need to. 98 newtons. Is this mass sinking into the ground like quicksand? Is it flying you like Superman? So there has to be an arrow pointing up. This is the normal force. Braden, exactly how big must the normal force be? Has to be. So if you look on your green sheet, you will not see an equation that says Fn equals some way of calculating it. Can't. But you can figure it out from a free body diagram. Darman, what are the forces acting on the second one? Get the obvious one. Okay, so let's label that. That's mg, and that was 98 newtons because it's the same mass. Is this sinking into the ground like quicksand? Is it flying like Superman? Am I going to draw the normal force pointing up bigger, smaller, or the same size as mg? And how do I know? Okay, something else is pushing down on this box. Maybe there's someone from off screen that's pushing down with an extra 30 newtons. So the normal force here, how would I calculate the normal force?
98 newtons and 30
It has to be.
But this is
By the way, really what that means is this is what you're feeling when you give someone a piggyback. When you give someone a piggyback, you feel heavier. Your mass hasn't changed. What has changed is the ground is pushing up harder on your feet than you're used to. And you think that means, oh, I must be feeling heavier. But I'm sorry, gravity hasn't changed on you. What's changed is the normal force required to keep you from sinking into the ground. But most of what you think is your weight, Jaden, is actually the ground pushing up on you. C. Nick, let's keep going. What was your name? Nick. Oh yeah, put your name with it. We have gravity down. 98 newtons. Is the normal force going to be bigger, smaller, or the same size as mg here? And convince me. Why smaller? Yeah. This would be, if you may have seen on movies when they're doing martial arts special effects, they're doing wire work, they blur the wire, they green screen the wires out after, but if you see the behind the scenes, the actors are wearing these wires to make them feel lighter. Their mass hasn't changed. What has changed? How hard the ground is pushing up on them. So I'm going to really exaggerate it. How would I calculate the normal force here? So here's the rule. You ready? If you're looking for kind of a normal force equation, are we sinking into the ground like quicksand? Sure no. Are we flying through like Superman? Sure no. Then forces must be, I'm looking for it starts with letter B. Really what we're saying is this. All the forces up have to equal all the forces down. That's sort of an equation, I guess. What are all the forces up? Well, the normal force and a 50. What are all the forces down? 98. How would you get the normal force by itself? Now, you might have been able to just say to yourself, do it. It's obviously 98 minus 50. But for a way more complicated situation, when in doubt, everything up has to equal everything down if you're not accelerating. How would I get the Fn by itself? Okay. Question for you. Braden, can I borrow you for a second? Could you stand up, please, my friend? I have here a bathroom scale. Could you stand on it? What does a bathroom scale, measure? What does it measure? Measure your mass? Let's see. If it measures your mass, I'd like you to watch the dial. Quickly do deep knee bends.
Oh, it's weight.
Really quickly. Is the dial moving? Did your mass change? So it can't measure your mass. Okay? I heard somebody say weight, mg, they're saying. Do deep knee bends? Did the scale dial move? Did gravity change?
No.
So a scale does not measure weight.
It measures force.
The question I have for you is, what does a bathroom scale actually measure? It doesn't measure mass. It doesn't measure weight. What do we call how hard the ground is pushing up on us? A scale measures normal force. So you ready? That means if I push down on Braden's shoulders, his mass doesn't change, but how hard the ground has to push up on him does, just like situation B. The scale should get bigger. Does it? Okay. If I were to lift up on him, has his mass changed? No. Has gravity changed? No. What force has changed? How hard what's the fancy name for how hard the ground has to push up? So, what does a scale measure, everybody? What does a scale measure? Everybody?
Normal force.
So on a test, when I ask you to tell me what a scale reads, what force are you going to find in your free body diagram? Normal force. So, a scale does not measure mass or the force of gravity. A scale measures normal force. By the way, when I jumped out of an airplane, when I jumped out of an airplane, if I stood on that scale in free fall, what would the scale read exactly as a number? Why 0? Because there's no ground pushing up on me. I still have my mass, and I'm definitely under the influence of gravity. Thank you very much. But I feel weightless because what you all think of as your weight is actually how hard the ground is pushing up on you. So when I ask you to find what a scale reads, what I'm really asking you to find is the normal force. That's one you want to commit to memory, because I guarantee there will be a test or quiz question in your future where I'm going to say, what does the scale read? Get the FN by itself. Okay. A good amusement park ride, roller coasters, all they do is they mess around with the normal force. They mess around with how hard your chair, the seat that you're on, is pushing up on you. So you can't change gravity. I have a lovely video here. This is a kid's first roller coaster ride. See if you can spot the moment when, for the first time, this kid experiences a changing normal force. Good high roller coaster. So again, your job is to see if you can spot when the normal force changes. If I had to make a guess, probably right around there. What's this kid feeling? Heavier or lighter? Half of you said heavier, half of you said lighter. The good news is some of you are correct. What's this kid feeling? Heavier or lighter? This kid's in a partial free fall. They feel lighter. And that's not something we have much experience with growing up. Growing up, all of you have had playground experiences where you feel heavier. If you piggyback someone, you feel heavier. At the bottom of a swing, you feel heavier at the bottom of the swing set. There are very few childhood experiences where you have a lighter than normal. You feel 0 normal if you jump off of a high dive, but many kids are too scared to do that. You feel no normal force on a trampoline while you're in the air, but that's no normal force. There's very, very few situations where you feel lighter than normal. This is this kid's first experience with that. Now, this is a video of a kid that's scared. I could never just leave this with you. Watch, this kid makes one of the best recoveries I've ever seen. I'm so proud of him. Because he is scared. He is really scared. But if you watch in just a few seconds, he's going to realize this is also fun. See if you can spot when that happens. Right there. And not only that, Wait for it. He even gets his hands up. Oh, that's a great recovery. That's a great recovery. Good coaster, nice and long.
Go again. Go again.
Go again.
Okay. So any amusement park ride, they just muck around with the normal force. Certainly any ride that goes up and down. Some of the ones that go sideways in a circle, there's a different force at play there. We'll talk about that next year. If you take Physics 12, we analyze centripetal force, circular force. But the rides that are going up and down, they're just mucking around with the normal force. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. Says this. A 72 kilogram man stands on a Newton scale in an elevator. What do I mean by a Newton scale? So the scale that we stand on displays kilograms. A Newton scale multiplies kilograms by 9.8 to get newtons. Okay? In fact, this scale measures the normal force and divides it by 9.8 to give you a kilogram equivalent. What does the scale read if the elevator is accelerating upwards at 3.2 meters per second squared? Ooh.
Acceleration.
First of all, Liz, what's this question asking me to find? What does the? Just read what does the? Stop. What's this asking me to find? The scale reading. What's this really asking me to find? This is asking me to find the normal force. Okay? That's the conclusion we got to get to. This is asking us to find Fn. So it's asking us to find the normal force. Is there also gravity in this question?
Yeah.
Is there more than one force? Somebody the other day said, how do I know when to do a free body diagram? Is there more than one force? This is a job for a free body diagram. I'm going to do the free body diagram in the margin right here. Liz, what are the forces acting on this person? Get the obvious one. Which way? Yep. What else? The scale pushing up on this person's feet, but what have we called that force? What does the scale measure? Normal force. Bigger, smaller, or the same size as mg, and how do I know? Which way are we accelerating according to part A? I'll exaggerate it so it catches my eye. Okay, you got the free body diagram. Who's winning? Liz, who's winning? Look at your free body diagram. You're way overcomplicating this. Who's winning? Who's losing? Here's our equation. Winner minus loser. What does winner minus loser always equal? What? MA. As far as I'm concerned, I can either give you the acceleration like I've done and say find the normal force, or I could give you the scale reading, the normal force, and you could find the acceleration. We would use Alex's theorem divided by m. But we're finding, how would I get the normal force by itself? Yes. mg plus ma, or ma plus mg, because we're adding the orders that make a difference. So it's going to be 72 times 9.8 plus 72 times 3.2. Because that one in my head, it's going to be 72 times 13. Maybe I can. It's going to be 72 times 13 is 720 plus 206. Is it 926? I'm totally wrong. Is it 926? No, what'd you get?
Pretty close. You're off by 166.
936? Carried a 1 wrong. Okay? So, What's this person's normal? mg. Can all of you go 72 times 9.8 on your calculators right now, please, really quick? How hard do they normally feel the ground pushing up on them?
105.6.
How hard are they now feeling the ground pushing up on them? Are they feeling heavier or lighter? Heavier. On the elevator, when it shoots you up, you feel heavier. If you were sitting on a scale and you had a chance to read the scale really quickly, you would feel heavier. In fact, take that 936. How do I change a force back into a mass? How do I change a weight back in? If they were standing on a kilogram scale, the scale would say that their mass was 95.5 kilograms. It's not, but that's what they feel their mass is right then. Okay? Is that all right? B is the same question as A. I'm going to leave it. If you want to try it on your own, you can, but it's also accelerating upwards. We're going to, because I got to cut corners a little bit, we're going to go to C, accelerating downwards. So first of all, what's part C asking me to find? Well, what's each question asking me to find, Alex? What does the, and when I say what does the scale read, which force am I really asking you to try and find? Okay, this is a job for a free body diagram. Alex, what are the forces acting on this person? Get the obvious one. Good. What else? How do I know there must be something pointing up? If there was nothing pointing up, what would this acceleration be exactly as a number? It'd be 9.8 free fall, baby, right? So I know there must be a force up, bigger, smaller, or the same size as mg. Which way are we accelerating? Which way direction is winning then? Downwards. So the force pointing up is going to be smaller. I'll exaggerate it so it catches my eye. Starting to see why free body diagrams are so handy. Who's winning? Who's losing? Equals. Yep. I'm trying to find the normal force. I want to get the Fn by itself. What's right in front of the Fn that I don't like? I'm going to do what I nicknamed the swappy dance last day. I'm going to plus the Fn to there, and I'm going to minus the Ma to there. You'd minus the Ma because it's got an invisible positive in front of it. And Parker, you're going to get Mg minus Ma. And Alex, do you mind, instead of writing equals Fn, can I put the Fn equals over on this side because that's where we're used to seeing a thing by itself? And now, plug and chug. It's going to be 72 times 9.8 minus 72 times 5.2. Do y'all get 331.2? Units, it's a force, Alex. Newtons. Yep. Oh, there's a second part. What would the scale read in kilograms? How do I convert newtons into a mass in kilograms? Divide by 9.8. So I'll quickly go divide by 9.8. Answer button, divide by 9.8. The scale would say a mass of 33.8. And that's why my argument is scales can't read mass, because if they read mass, it shouldn't change, because the person's mass hasn't changed. What does a scale actually measure? Normal force. Question, Marley? Okay? Yeah? D is the same question as C, accelerating downwards. And normally I would do it, but because I have a shorter class, I'm going to skip D. You can try it yourself if you want. E. E. Okay. Malcolm, what does E want me to find? What does every one of these questions want me to find? Which, okay, and this is a job for her. What are the forces acting on this? Get the obvious one. What else? What else? Which way? Bigger, smaller, or the same size as mg, and how do I know? Okay? Okay?
We're finding normal force, correct?
We're finding normal force. Are you ready? If you said smaller because it's moving downwards, you're wrong, but you're still okay, as long as you don't work for Verizon. So we're going to do it wrong to show you that the method that I'm teaching you, as long as you don't work for Verizon, will still bail you out. So you said, I'm going to make it smaller. Okay. So what's our equation? Who's winning? Who's losing? What does winner minus loser always equal? MA. How would you get the FN by itself? What's right in front of the FN that I don't like? Okay, do a swappy dance. And you would get MG minus MA. And now we're going to find out which ones of you work for Verizon. So let's plug and chug. Malcolm, what's the mass? What's G? What's the mass? What's the acceleration? What? Oh. What two-phrase word should I have underlined right away? I should have noticed that. It's a tie. Forces must be. I'm looking for a word that starts with letter B. And so you could have just said, hey, the normal force is the same size as mg. But do you notice, even if you missed that, as long as you don't go work for Verizon, as long as you're careful with units and don't put a meters per second in for a meters per second squared, you get the final result anyhow. You just wasted a line of writing. But the nice thing is it's self-correcting as long as you're careful. I would have said constant velocity, it's a tie. Normal force is mg. By the way, this is hugely important. Albert Einstein said there is no experiment in the universe that can detect if you're moving at a constant velocity or if you're at rest. We can't tell the difference. Are you all at rest right now? No, you're not.
No.
Earth is not at rest, but because it's moving at a constant velocity, can't tell.
So if it started accelerating, we just be like, oh.
Exactly.
If it started accelerating, your body's inertia would make you feel like you're getting pushed in the opposite direction of acceleration, which is why your bodies are backwards accelerometers. What is 72 times 9 point? I can do that in my head. It's going to be 720 take away 14.4. So 720, 705.6?
Yep.
Okay. This is kind of neat. What all of you think of as your weight is the normal force. We can muck around with that. In fact, we can even set it up so that the normal force, well, let's see. F. What if we're accelerating downwards at 9.8 meters per second squared in free fall? Well, what's this question asking us to find? This is a job for a free body diagram. What are the forces acting on it? Get the obvious one. Okay. What else? Well, normal force. Which way? Up. Which way are we accelerating? So I will draw the normal force smaller. It's the loser. Who's winning? Who's losing? What's it going to equal? MA. I need to get the normal force by itself. Swappy dance. I would encourage you, draw the arrows. I find drawing those two arrows cuts down on silly mistakes. Go figure, but it does. The mg drops down like a domino, but the MA goes where the normal force does, and I'm going to put the normal force right there. What's M? 72. What's G? 9.8. Minus, what's M? 72. What's the acceleration in this question? No. We took care of our negatives and positives by going winner minus loser. What is 72? Don't need a calculator, Aiden. What is 72 times 9.8 minus 72 times 9.8? What's the normal force? You would feel, if you were in an elevator that was in free fall, you would feel exactly like astronauts floating in space. In fact, this explains why astronauts on the International Space Station float. They don't float because there's no gravity. What holds the moon in place around the Earth? If Earth's gravity reaches the moon, I assure you, Earth's gravity reaches the International Space Station, which is way, way, way closer than the moon. There is gravity up there. You can calculate it. It's not 9.8, it's about 9.2. But they're floating. Why are they floating? It's not because they have no weight. It's because they have no which force? No normal force. Why do they have no normal force? So I wrote down here, it isn't that there is no gravity, it's that there's no Fn. Okay? Remember, another name for the force of gravity is weight, and another name for the normal force. A nickname we give the normal force, we call it your apparent weight, the weight that you feel. And on the International Space Station, the normal force, the apparent weight, is equal to 0 newtons. Why is there no normal force?
There's no ground to push up on.
Why is there no ground to push up on them?
In space.
No. There's a surface on the International Space Station. Why don't they feel the ground pushing up on them? Here's your hint. See F above.
They're constantly accelerating downward at 9.8
They're in free fall. So the real question isn't why do astronauts float? They are in free fall. Why doesn't the International Space Station crash into the ground? That's the question.
Is it a free
Okay.
fall sideways?
No, they're free fall straight down.
Yeah, why isn't it what?
Oh, because their boosters are pushing
Nope.
them the other way.
So,
Wait, that doesn't mean that they stand.
Earth. This is one of Isaac Newton's famous thought experiments. I'd like you to imagine we have a big mountain on the Earth, and on the mountain we're going to put a big cannon. It's going to fire a cannonball. Boom, lands there. What if we put in more gunpowder? Boom, might land there. What if we put in more gunpowder? Boom, might land there. It's always falling to the Earth. Yes, it's in free fall, but it's also moving sideways. Isaac Newton said, I'll bet you there's just the right amount of gunpowder where when we fire the cannon, boom,
You'll hit A.
it's continually falling closer to the Earth, but never getting closer to the Earth because we give it just the right sideways velocity. And we call this an orbit. Okay. We'll look at orbital mechanics in Physics 12, but the reason the International Space Station astronauts float is not because there's no gravity, it's because they're in free fall.
They're in the orbit.
The reason they don't crash is because we spend a lot of our rocket fuel pushing them sideways. And in space, because it's a vacuum, once we get them going, Newton's first kicks in, they'll keep going in a straight line at a steady speed. We don't need to continually boost the rockets. There's a tiny bit of atmosphere up there. I showed you a video of the ISS doing a rocket boost. Every couple of months, they do have to do a gentle boost. But for the most part, it works like that. You can do this near the Earth, too. If instead of outer space, if you get into an airplane and the airplane dives down at 9.8 meters per second squared, you will experience weightlessness for a short moment. You will float like an astronaut for a short moment. NASA trains their astronauts in a jet like this. Does anybody know what nickname the vomit comet, because you throw up. But there are also tourism companies that offer this.
That must smell terrible.
The band OK Go did a video a couple of years ago where they chartered a Russian version of the Vomit Comet. So your job is to see if you can tell when they're accelerating down at 9.8, when there's no normal force, and when there is a normal force. Put your pencils down, look up.
Zion vomit?
Okay, go upside down.
They're level flight right now. Diving down. And they get about 20 seconds of weightlessness, and then what they're actually doing is they're freezing their position while they pull back up, but they're not recording. And then when they dive down again, they're hitting record again, and they're just merging it with some good merging technology. So you can see things have landed on the ground in the back there. They've just started to pull up for a bit. Diving down. Pulling up and freezing. Diving down. You saw them kind of thump down there, so they're pulling up, holding their position till they're at the top again, and again, diving down. There, wait, you can see there was a normal force. They were walking normally, so they're pulling up. Pulling up, now they're walking normally again. There's weight again.
Inside down, upside up, and you can feel it, feel it. Don't stop, can't stop, it's like a freight train. Don't stop, can't stop till you feel it. Go down. I wish I had said this is all that I had said. Gravity's just a habit that you're pretty sure you can't fake. Upside down, inside out, you can feel it.
Was there gravity in that whole video? Yes. What force was briefly being turned off? The normal force. But that's what all of you think of is your weight. He was not doing well. You can even see it in his face here. They spent a week making this, and he was throwing up an awful lot. There's a good YouTube video where they look at the backstory. And this was their last day. They nailed the take. They thought they had it great. And then when they watched the re-video, when that first orange balloon popped, the ink covered the camera lens. And they were, and so you can see they had to talk him into going one more time because he was throwing up all the time and just not feeling well. But it's a really neat video. Very well done. Good physics.
That was good.
Last question. I like example 5. I like example 5. I like example 5. Again, we have a person standing on a scale in an elevator. I call these elevator questions, and you're going to get elevator questions on your test. Somebody standing on a scale in an elevator. In the previous questions, I gave you the acceleration, and we said find the normal force. What are they asking us to find here in example 5?
The magnitude of the direction.
They're asking us to find acceleration. Okay, there's 2 questions. I'm going to do a little line like this. Okay. This is a job for a free body diagram. So What are the forces, Sarah, acting on this person? Get the obvious one. Which way? Good. By the way, what's this person's mass, Sarah? According to part A, what's the scale saying this person's mass is? Loud and proud. What's the scale saying this person's mass is? Okay. Is this person feeling heavier or lighter? Which way are we accelerating? Okay, the good news is it's down or up. So, which way are we accelerating if we feel lighter? Which, first of all, if the scale, which is also the normal force, is smaller than that mass, the normal force is smaller, we're accelerating down. So let's draw a smaller arrow pointing up. You'll feel heavier accelerating up, you'll feel lighter accelerating down. Sarah, who's winning? Who's the loser? What's that going to equal? What am I trying to find? How would I get the A by itself? Alex's theorem. Okay, now this is a little bit tricky, so make sure you're paying attention here. Sarah, what's the mass of this person? 45. What's G? 9.8 minus, what's the normal force? How do I know it's not 32? If 32 was a force, what units would be next to it? Newtons. What does it say? I gave you the scale reading. How do I convert kilograms into newtons? It's going to be 32 times 9.8. That's what the normal force must have been. Divided by, Sarah, the correct mass, the actual mass. 45. So this asked for magnitude and direction. We already figured out the direction. You're feeling lighter, so which way are we accelerating? I'll put the word down so I don't forget to include the direction. Is this a fraction? Is there more than one thing on the top? Oh, and we're not in free fall, so we're going to get an answer less than 9.8. What do you get? Jordan, what'd you get? Sorry? 2.83? Anybody else?
Yeah.
Sorry, 2.833. So 2.83. And units, it's an acceleration. So as far as I'm concerned, for an elevator question, I can either give you the acceleration and say get the normal force by itself. That was all of these ones. Or I can give you the mass and say the normal force and say find the acceleration. Let's do B together. This is a job for a free body diagram. Yeah. I got the word down there. It said magnitude, which means just give me how big it is, and direction. So don't worry about positives and negatives. What are the forces acting on this? Get the obvious one. Good. What else? There has to be. If there wasn't, then if there was no normal force, what would the scale read exactly as a number? 0. It doesn't. Is this person feeling heavier or lighter? Which way are we accelerating in the elevator then? I'll exaggerate it so it catches my eye.
That number wins.
It's winning. Who's winning?
FN,
Who's losing?
MG equals MA.
What am I trying to find?
A.
Get the A by itself, Alex's
Right.
theorem. How do I find the normal force? Well, a scale measures normal force but converts it to kilograms. So it's going to be 64 back to newtons and then minus 45 times 9.8.
Isn't that strange? Isn't that fun?
Oh, up. I'll add the direction. What do you get?
4.14.
4.1? 4.14? 4.14 rounded off properly?
Yeah.
Sure. By the way, most elevators accelerate less than 1 meter per second squared, so I'm making some pretty entertaining elevators just so we get some interesting numbers.
How many G's?
About half a G, right? 10, so 5 would be half a G, a little less than 5. And this is what we mean by negative and positive G's. So in the first one, you'd be pulling negative G's because you're feeling lighter. In the second one, you're pulling positive G's because you're feeling heavier. That's weight, mg. That's what a scale reads. What does a scale measure? Normal force. And that's elevator questions. Yes?
Why when the value up there and
Because it said magnitude and direction in the instructions. That's the only reason. I read the question carefully and, oh, okay. If this was a test question, I probably would have underlined or bold fonted the words magnitude and direction.
then the rest is one, right?
Direction is,
The one.
yeah, yeah. So, homework. Number 1, 2, 3. You know what? It's going to be every question. So, all of those, and then these elevator questions. Okay? So, the first section is just asking, do you understand the difference between mass and weight? I put the answers at the bottom of the page. And then here, number 1, I'm giving you the acceleration, find the normal force. Number 2, I'm giving you the scale reading, find the acceleration.